Hello, welcome to this week's video for the PowerPoint. Again, wanted to provide just some talking points in regards to this week's content. And really we're going to be talking about conceptual foundations of statistics. But I just wanted to preface this week that it's not the intention of this class to really teach statistics or to test you on statistics or test your statistical knowledge. And so I know each of you bring a background where you probably took a statistics course in your undergrad and master's, and you'll probably take one in your doctorate if you haven't already. And so I'm really just going to go over the conceptual basic elements of this week's content without getting into the depth of it and where it's usable and the purposes of this class. I will provide some additional links for if you need more information about that, or a refresher or a reminder, or want to learn about it. I'll have some video YouTubes that you can watch. They're really great tutorials about that content area. So let's get started. I wanted to break this week's chapter really into two different component parts, and Hoy doesn't necessarily do that. But I wanted to first talk about descriptive statistics. And really, when you get a set of data and you work with numbers, you're attempting to describe the group by calculating different things, and you're trying to describe what the group was doing in regards to that outcome or whatever you were attempting to measure. So statistics of a group, they're attempting to describe that population, and often that group is a sample, and we'll talk more about samples and populations. But I wanted to first start out talking about what are some descriptive statistics that we often approach, and how it is different than inferential statistics that we'll talk in a minute. But the most common one are measures of central tendency. And you've heard mean, median, and mode. You're probably very familiar with them. And the mean being the average, taking all the numbers, dividing by the total possible number, and you get a mean, you get an average. The median being the very middle, the center of the data. If you could cut the data in half, it would be the median number. And mode is the most frequently and most common occurring number within that set of data. And each of these have their strengths and each of them have their weaknesses, as a mean is often influenced strongly by outliers and can really pull the mean one way or the other depending upon those outliers. The median is beneficial because it can tell us the middle if we were to divide the data in half, where that middle data or that middle number is in that range of numbers. But it's also influenced by the numbers and outliers. Mode is good because it can tell us the most commonly occurring number. If we wanted to know, how many people or the most commonly occurred or selected on a survey or of a 0 to 10 scale, and most often people pick the 6 versus the average of a 2. It's important to know that, but the mode is also influenced by the number of people that pick an individual number. So these are attempts to provide a one number summary of a set of data. But can one number really capture it all? And I would argue no. That the mean is just the beginning in an attempt to describe the data. Really, in quantitative, what we celebrate is the variability, and that's why often people are drawn to quantitative research, is because we're attempting to describe the variability of a set of data and how it approaches or how it attempts to describe the population. So one thing we look at often is the range, the distribution of all the scores, all the potential possibilities. So we have the lowest to the highest, and we can calculate a one number summary for the range, telling us that from 0 to 100 we had 100 points, or if it was 50 to 100 we have 50 points. That range is telling. It tells us something about the data set. And that's one attempt to be descriptive. We can use many other charts, diagrams, things to show that, frequencies, and so on. Another thing we look at are average deviations, and deviation meaning of how each individual response deviates or is different from that mean or center number. So it's all in relation to the mean. Now the problem with average deviation is if we were to do that calculation, it's always going to equal the same number for every sample. It's always going to be the same because it's going to be 0. We know that on one side of the mean and the other side, if we add those, We have negative and positive, and it'll always balance each other's out, and we'll have 0. And that's why we most often use standard deviation, because we square those numbers and it gives us a positive number. It also gives us a conversation to know how these objects or how these numbers vary about the mean. And we also have 1 standard deviation, 2 standard deviations on this distribution, on this plot. If you'd like to see an example, Khan Academy gives a great example of standard deviation here. Excuse me, so you can click on that link. But let's talk distribution. Here's a normal distribution. You can see most of our data is here in the middle, and then it comes out to the edges, often called bell curve. Maybe you're familiar with that. But you can see that the normal, this normal distribution, 0 here being the middle is our mean. Whether this is the true mean or the sample mean, the population mean, this is the middle part of the data. And on each side are standard deviations, and +1 standard deviation, -1 standard deviation. So within the standard deviation is 68% of the data. And then to 2 standard deviations is 95, and to 3 standard deviations is 99. And so this is telling for us is that when we say that the points or this data is 2 standard deviations away from the mean, we know that it was pretty far out from the mean or from the average. And so having this graphic really shows where most of our data is going to fall. And so this helps us identify that probability or that chance that we know if we see observations that are outside, it's more likely not due to chance, or it is due to chance. But it shows us where the normal or most of the data fall. I really like how Hoy included these subsections so that we can break into component parts, that we know these tails. And that'll come into play later on as you get into statistics where you talk about 2-tail or 1-tail tests. So let's talk briefly about population and sample. We're always attempting to describe the population. And the population really is all members of a particular group. So if we're talking students in the United States, that's our population. But the reality is we can't really measure every single student in the United States. So we often take samples, and it's a more feasible, cost-effective way, realistic way of approaching that. So we use sampling techniques to attempt to identify a sample that is most representative of that larger group. And there's a lot of different nuances and techniques to doing that, such as simple random sampling, stratified sampling, that help remove bias in selecting a group. It also provides credibility and reliability in our statistical numbers later on into how we sampled. And that's important to know, as in descriptive statistics we're just describing what we have. But then we're going to move into the inferential statistics, where we're attempting to infer to a population and to a larger group. But it comes down to this question, and this is the basic statistical question that Hoy presents, is within my research, is what I found or what I saw significantly different from what I would expect to find by chance? And you're probably saying, well, that's the null hypothesis. Yeah, essentially that is that what we observed is it different than what we expected to see. And this is really the grounds for our inferential statistics, is what we see significantly different than what we would expect to see for that sample or for this population. So those descriptive statistics are applied to populations. And statistics really are characteristics of a sample, which then are attempting to describe the larger population. And when we use the word parameter, we're now describing a population. So we're hoping to come up with a population parameter. And so I'm going to talk briefly about a number of statistical tests, or inferential statistical tests, that Hoy highlights here. The first one is the t-test. Often 2 types of t-test, a paired or independent t-test. But I'm just going to talk general t-test, is where we deal with an independent variable that has 2 categories. And they're either a nominal category or an ordinal category, but they're categorical variables, the independent variable is. But the dependent is continuous. It's a ratio or interval type data. And so we want to compare whether these 2 categories are significantly different from each other. And so we get what's an output called a p-value. And the p-value is the probability that the results or a function of chance. It's really going back to this question here, what I found significantly different. It's that measure of that significant difference. And if we have a p-value of 0.01, that's a 1% chance, or 1 times out of 100 that observation that we saw will occur out of 100 times. So that p-value gives us interpretation in interpreting a test. So an example for t-test, you can go here to the YouTube. It walks through a great example here and goes through the calculations and shows you how you would possibly use a t-test. But really the essence is you have two categorical variables or independent variables that you want to compare to see if they are different from each other. So let's move to what if we have more than two? So we have three groups or three variables. They're all the same variable, but they're three different groups within that variable that we want to compare using a continuous dependent variable. So let's take the example of we have one math program that we're teaching. We have three teachers that are teaching it, and we want to compare whether there's a significant difference between these three teachers and how they're teaching this math program. So the variable is the same as this math program, but the groups are different as we have three different teachers, and the manifestation of those teachers are the student scores. And so that's that dependent variable there. And we can compare those and come up with a significant difference between or within those groups. Another example here, if you want to go to that YouTube, it walks through and actually goes through pretty detailed of how to calculate those. The nice thing about these tests is that we don't necessarily have to use a calculator and calculate them ourselves, as we have statistical tools that will calculate those for us, but we need to understand how to set them up. So those are two tests that are the independent variable is categorical and the dependent is continuous. And depending on your number of groups, whether you want two or more than two, you would select the t-test or the f-test. So now what do we do if we have two categorical variables? Our independence categorical and our dependence categorical. Can we compare those and see if there's a significant difference? Yes, we can. And really it's using frequency. So let's take the example of gender. We want to compare gender in how good we are at directions. So we're either good at directions or bad at directions. We're male or female. And so we compare what we expect versus what is observed. So we would expect, 50% male, 50% female, 50% good, 50% bad, and then what we observed, and we compare that frequency with these frequency counts. And we can get a statistical number to tell us whether or a significant difference between those two. Now, in the last three examples of tests, we don't necessarily talk about magnitude, and we can't see the relation from the independent on the dependent. And there is a statistical test we can do which incorporates the effect size that will help us determine the magnitude of the influence from the independent to dependent. And that's when we're dealing with independent categorical variables. But when we deal with continuous variables, the correlations themselves will indicate that magnitude or strength of relationship. So in talking about two types of tests, the first one is correlation, where we have one continuous independent variable and we're comparing it to one dependent continuous variable. And we, as for an example, so if we think x and y, as x increases, y increases. As x increases, y decreases. This will give us a product or an R value, which will tells us the strength of that relationship. This is often called the Pearson's R correlation coefficient, or R value, which can be from between +1 to -1. +1 meaning a positive, perfectly correlated, strong relationship, and 0 being no correlation, and -1 being a negative correlation, strength of the relationship. And I encourage you to watch either of these two videos. This creative one is kind of fun. They use dance to explain correlation, but to enhance this, please see these videos. So what do we do if we have more than one independent variable? Can we run a correlation then? So we can run a multiple regression or multiple linear regression when we have more than one independent continuous variable and one dependent continuous variable. And so like the correlation where we had the R value, in the multiple regression we also have another R value. This is the capital R, and it's just explaining how much variance of the dependent is explained by the independent variable. But with an independent variables, if we have more than one in the multiple linear regression, we often want to know the impact of all of those variables. So how much of that variability? So we have a line often that we'll draw with those multiple variables. And how much variability is explained by that line is the R squared value. It's essentially squaring that R value, and it tells us the strength at which that line describes those points that we observed. And so multiple regression is great when we have continuous variables. Oftentimes we'll incorporate, if our dependent is student outcome and we want to test socioeconomic status, if we want to test IQ and so on, we have multiple continuous variables and we can see that influence on that outcome, that student achievement. One thing I wanted to pause here and highlight, that oftentimes correlation does not equal causation. And I want to reiterate that over and over, and that's really why I assigned that reading Freakonomics. And I love those books because oftentimes we go to an assumed knowledge that what we see is causation, and it's not always the case. So I encourage you to watch this video here. This is actually the authors from Freakonomics talking about what you read about pool versus guns and the correlations there. But often, or I want to provide caution here, is correlation, when you see a strong correlation, it doesn't necessarily mean that there's a causation, and we have to qualify that. It's important to highlight here. So just in summary, Hoy reiterates at the end about choosing the right test, and it all comes down to how we operationalize those variables. That independent and dependent variable, if they're continuous or they're categorical, really will help us select the appropriate statistical test to test the significance of those two in that relationship. And the 5 that we've talked about really are only scratching the surface as to consider the types of statistical tests that are out there. There are statistical tests to utilize when you even have 2 dependent continuous variables. We didn't even talk about that, logistic regression. There's also when we don't follow a normal distribution. What can we do? There's manipulations. There's all types of statistical tests. But really, these are the 5 that are the most common and are most often used. And just wanted to highlight that for you, that there's multiple tests that you can select and choose. But these are probably the most that we'll use and work with, especially in this class. So I hope that was helpful. If you have any questions or concerns, be sure to email me or give me a call. Thanks.